In this lecture, today we are going to discuss a very important application of Bose-Einstein statistics. Actually, this is regarding the liquid helium 2, or you may also say that this is the problem of superfluidity of liquid helium 2. Actually, liquid helium 2, you will see that this is called a superfluid because of some of its strange properties. Okay. So, the theoretical basis of explanation of the behavior of this abnormal behavior or anomalous behavior of liquid helium 2 we have already studied in the previous lecture. So we will discuss the theoretical aspect by writing the results obtained in the previous lecture directly. Okay, you know that helium is an inert gas and it has two isotopes. Definitely this will be in your knowledge. The first one is He3. It means the mass number of the first isotope of helium is 3, and the another isotope is He4, whose mass number is 4. As you know that any nucleus which has actually the odd mass number, or any atom which has odd mass number, that has half integral spin, and they are actually fermions because they obey the Fermi-Dirac statistics. So you can see here that the isotope He3, which has a mass number of 3, and 3 is an odd number, so definitely He3 will have a spin half, and it will be a fermion obeying the Fermi-Dirac statistics. Okay. On the other hand, you can see that He4, which has a mass number of 4, which is an even number, definitely this will be a boson, and if it is a boson, then it will have integral spin, and it will obey the Bose-Einstein statistics. Actually, this isotope He4 has a spin 0. Okay, and it obeys Bose-Einstein statistics. Okay. Now we are going to discuss a particular problem of this helium in this lecture. This is regarding the fluidity of the helium liquid. When you say fluidity, it means you know that when the temperature of a liquid is decreased after a particular temperature, which is the liquid actually becomes solid. But this fact is not seen in case of this helium liquid at normal atmospheric pressure. Actually, for the phase transition, actually the pressure and temperature both must be controlled. So if you will try to solidify the liquid helium at normal atmospheric temperature, you will be not successful, because if the temperature of liquid helium is lowered even to absolute zero temperature, that is 0 Kelvin temperature, at normal atmospheric pressure, that is 76 cm of Hg. So at this pressure, even lowering the temperature of this helium liquid even at absolute zero temperature, the helium liquid does not solidify. Okay, it remains liquid. If you want to solidify the helium liquid, then you have to increase the pressure at least up to 25 atm. It means the pressure must be greater or equal to 25 times of the normal atmospheric pressure. Only then, after lowering the temperature, this helium liquid will get solidified. So this is a unique character. Okay, and Actually, as there are two types of isotopes, so there will be two types of a helium liquid. One will be He3 liquid and another will be He4 liquid. Okay. But since, as you have seen, that He3 obeys Fermi-Dirac statistics, while He4 obeys Bose-Einstein statistics, since the statistics obeyed by these two isotopes are different, so definitely the physical properties of these liquids, that is He3 liquid and He4 liquid, will be definitely different. Okay. Actually, as you are studying here the Bose-Einstein statistics, so our prime aim is to discuss the unique properties or the strange properties of the He4 liquid. Okay. Actually, He3 liquid is just a normal liquid, but He4 liquid, you will say that it will have actually two phases, and in first phase actually it behaves as a normal liquid, but in second phase it will possess some strange properties which actually does not found in any normal liquid. And the transition of helium liquid from one phase to another is just a second order phase transition. So this is also a problem of phase transition, that is second order phase transition. Okay. Now, first of all, we will see what are the causes behind this fluidity of helium liquid. Why this helium liquid does not get solidify at normal atmospheric pressure, lowering the temperature even up to 0 Kelvin. What are the reasons behind this? We will see now. Okay. Actually, there are two main reasons or two main causes, you can say, for the fluidity of helium even at very low temperature. There are two reasons. The first one, you can say, this is weak interaction, and the another is a small atomic mass. When you say weak interaction, it means the interaction between the atoms of He4 is not strong, but it is weak, and its atomic mass is also smaller. Okay. Actually, when the helium is in its lowest energy state, you know that the lowest energy state is also called 0 point energy. Okay. It means when the temperature of this system is 0 Kelvin, and at that temperature, you know from quantum mechanics, the system possesses energy, its energy is not zero, and that energy is actually minimum, and that very energy which is possessed by the system at 0 Kelvin temperature, that is called 0 point energy, and it is the lowest energy of the system. Okay. In fact, this helium has a large 0 point energy, but as I have told you that in this case, there will be a weak molecular interaction. In the one hand, the 0 point energy is very large, and on the other hand, the molecular interaction is weak. And that's why it is impossible to localize the atoms at well-defined lattice sites. You know, in case of a solid, or particularly a crystalline solid, you know, the solid has a definite or a particular geometrical structure. The lattice points are at definite locations. Okay. So whenever the atoms will be set, atom will be localized at definite positions, only then liquids become solids. Okay. But as in this case, localization of atoms at definite positions is quite impossible at normal pressure. Why it is quite impossible? The reason is what? The reason is the 0 point energy is large. It means even at 0 Kelvin temperature, there will be a molecular vibration, okay, in this case of helium. On the other hand, the intermolecular interaction is very weak. So the atoms do not get localized at definite positions. And since for a solid, the atoms must be at a definite position, and it is impossible in case of helium because I have told you, due to the large 0 point energy, large vibrational energy, and a small molecular or weak molecular interaction. And that's why it becomes impossible to localize the atoms at well-defined lattice sites. And this is the cause that helium does not get solidify at normal atmospheric temperature, even at a very low temperature, even at 0 Kelvin temperature. Okay, this is the reason. Okay, one may think that such property should be exhibited by other inert gases, other noble gases, but it is not correct. In fact, the other noble gases like argon, this can be solidified at a very low temperature, okay, without exerting a very high pressure. This can be solidified. Why this noble gas like argon gets solidified at very low temperature? The reason is that this the atom of the argon has a smaller 0 point energy, not large 0 point energy. So it is possible to localize the atoms of argon at definite positions, and it easily gets solidified. Okay. Now you can think that for fluidity, a small atomic mass is also responsible. So you can think that hydrogen is lighter than helium. So hydrogen should also not get solidified. But that is not the actual situation. Hydrogen is, although lighter than helium, its atomic mass is smaller than helium, but it gets solidified. The reason is that in this case of hydrogen, the molecular interaction is very strong. So although its atomic mass is small, but due to the strong molecular interaction in case of hydrogen liquid, it is possible to localize the atoms at definite positions, and so hydrogen also gets solidified. So you can think that what are actually the reasons behind the fluidity of this helium. I think we have definitely understand. You should have to tell that due to large 0 point energy and weak molecular interaction, it becomes difficult, it becomes completely impossible to localize the atoms of helium at a particular lattice site, and that's why this helium liquid does not get solidified at normal atmospheric pressure, even at an extremely low temperature. Okay, this is the cause of fluidity. Okay, now we will see a particular phenomenon when this helium liquid actually passes from one phase to another, and that is actually called lambda transition. As you know that helium when it is in the liquid form, there will be actually two phases of this helium liquid. Actually, this phase transition diagram I have shown here. You can see this is actually the phase diagram of He4 liquid, as you can see it here. Okay, actually in this phase diagram you can see that a peculiar property of He4 is that it has two liquid phases, which is actually called He1 and He2. You can see I have plotted a graph here between P and T. P is the pressure and T is the temperature. You know that phase transition or phase diagram is a graphical plot of pressure in against of temperature. Okay. Now you can see that when this T is equal to 0, this at this origin, and P is also 0, the helium is in gaseous state. You can see just in gaseous state. This is gas helium because pressure is also very small. Okay, but as the pressure increases, okay, pressure increases, and you can see that increasing the pressure and decreasing the temperature, the helium is transformed into liquid state. Okay. In fact, in this figure, you can see that at this pressure 2.26 of atm, this point which I have shown here, this is actually the this is called actually the critical point. Okay, this is critical point. Okay, and this line which I have this vertical line, you can see this is actually the line of lambda transition. Actually this lambda transition means the graphical plot is of the shape of lambda, so this is called lambda transition. Okay, and before at corresponding to this lambda transition, the temperature is 2.18 Kelvin. This value is experimental value. Okay, and before this temperature, this helium liquid is in a particular phase which is called helium 1. Actually this helium 1 is a normal liquid. It has no peculiar property. But after this temperature 2.18 Kelvin, it means if you will lower the temperature from 2.18 Kelvin, then this helium first is transformed into a new phase which is called helium second. And this helium second is not a normal liquid. It is a superfluid. It is a superfluid. Why it is called a superfluid, just we will see. Okay. And this helium 2 which possesses actually some peculiar or strange properties remains in the fluid state, in the liquid state when the temperature is up to 25 atm. You can see the figure. Only when, not temperature but pressure. But only when the pressure becomes greater than this 25 atm, then you can see that this solid helium is formed. That is, the liquid helium is converted into the solid helium. But above pressure 25 atm. Okay. Now, as I have told you that this temperature T lambda will be 2.18 Kelvin. This is actually the experimental value. Okay. Now, in fact, this helium 2 has some peculiar properties or strange properties I have told you. And one thing, again I am repeating, that the transition of this helium first into helium second, this is just a second order phase transition. So it does not take place at the cost of heat, but you can say that in this case actually the structure or the structure or crystal structure of this system gets changed. Okay. Now, what are the peculiar properties of this helium second? We will now see. Actually, in 1908, a famous scientist named Camerling Ons, first of all, liquefied helium. Okay, And after his experiment, when he liquefied helium, then it was found by uh, his co-workers that below a temperature of 2.18 Kelvin, this helium liquid shows some specific properties, some strange or peculiar properties. Okay, they observe. Actually, uh, in fact, you can say that what are actually the strange properties of this helium second, you can see. If you let us consider that this helium liquid is taken into a beaker. Let us say this is your beaker, and in this beaker actually helium liquid has been taken. Okay, and this beaker is not completely filled. Okay, in case of normal liquid, you know that if the beaker is half filled or 1/3 filled, the remaining part of the walls of the container will remain dry. Okay, but if you take the helium fluid inside this beaker, it is seen that the helium liquid actually crawls over this wall, this crawl up walls, and coat all inside surfaces of its container. Okay, and if it is placed in an open beaker, the liquid will crawl up the wall, across the rim, and out of the beaker. So this will drip. This will be dripped from outside wall. So this is a very strange property. Such property is actually not seen in case of a normal liquid. And that's why we simply say that the helium is a superfluid. It is a superfluid. Okay. Now I have actually mentioned here some of the important strange properties of this helium-2. Actually all these strange properties are shown by the second phase of helium liquid, not helium first. Helium first, as I have told you, that is just a normal liquid, but helium-2 possesses these peculiar properties. Okay. So what are some important strange properties of this helium-2? I have actually listed here. You can see the first one is its entropy is zero. Its entropy is zero. It means the entropy of helium second is zero. Its viscosity is zero. It means there is no internal friction in case of helium-2. And as its viscosity is zero, so when you will take let us say a tube, and this tube is of a very small bore, its diameter or its radius is very small. This is just a narrow channel, you can say, and its radius or diameter is smaller than 10 to the power minus 2 centimeter. So this is a very narrow, extremely narrow, you can say, channel. Okay, but even through this narrow channel, this helium liquid flows without any resistance. Without any resistance, this helium liquid will flow through this channel. Although in case of a normal liquid, you know, whenever the liquid will pass through a channel, it will feel resistance due to the because it has viscosity. But its viscosity is zero, so that it flows with no resistance through a channels of extremely small diameters. Okay. Now, in case of helium second liquid, when heat passes through this liquid, that behaves like a wave. It means heat propagating through helium second liquid behaves like a wave, and it moves with a definite velocity. This heat flow takes place with a definite velocity, and it behaves like a wave. Actually, this wave is also called second sound. Actually the problem of second sound is a separate problem. It is also a very important application of Bose-Einstein statistics, which we will see in the forthcoming lecture. Okay, so these are some specific properties, some strange properties of this helium second liquid. Okay, now we will see the explanation of the anomalous behavior of helium second on the basis of molecular theory. Okay, actually you know that the helium liquid has a weak intermolecular interaction, as I have mentioned you earlier, and the helium atoms may be regarded roughly as moving freely in a constant attractive potential. We may assume it. In fact, London has developed the molecular theory for this helium second, assuming that this helium 4 is an ideal boson gas, and this obey Bose-Einstein statistics. Okay, so how theoretically on the basis of molecular theory we can explain it? Now let us see. What I have mentioned, you can see I have written here for your convenience, because this will be a good notes if you note down this lecture in your notebook. Okay, so pausing the video, you can note down in all these things in your notebook, and then it will be very clear to you. Okay, now as I have told you that London assumed that the liquid helium 4 is an ideal Bose gas and it obeys Bose-Einstein statistics. Okay, now if we treat that He4 is a spinless ideal Bose gas, it means its spin quantum number s is equal to 0, and you know that the spin degeneracy factor Gs, which is given by 2s plus 1, and since s is equal to 0, so this spin degeneracy will be equal to simply 1. Okay, so if we assume that the spin degeneracy of He4 is 1, in that condition what will be actually the value of critical temperature? We have already calculated in the previous lecture on Bose-Einstein condensation. You have definitely watched that video. And so I am writing this expression directly here. You can see the derivation of this result in the video on Bose-Einstein condensation, which I have already published earlier. Okay, so you know that if Tc is the transition temperature, that is you can say the critical temperature where this transition from helium 1 to helium 2 takes place, then this critical temperature is given by what? This is given by N divided by zeta 3 by 2 times V whole to the power 2 by 3 into h square by 2 pi mk. I hope you have definitely this expression in your mind, because you have studied this in the lecture on Bose-Einstein condensation. Okay, so I have written it here directly. Okay, this is the value of critical temperature. Now you know that this Riemann zeta function zeta 3 by 2, this is equal to actually 2.612. So instead of this zeta 3 by 2, you may also write 2.612. Okay, now we can estimate the value of this Tc by considering the value of this N by V, which will be actually the number density, the value of this zeta function, the value of H, M and K. Actually H and K both are, you know, universal constant, and definitely their values in your mind. K is Boltzmann constant and H is Planck's constant. So let us take the mass of the helium atom is equal to 6.65 into 10 to the power minus 27 kg. And we considered a volume V equal to 27 into 10 to the power minus 6 meter per cube. Okay. So roughly this N by V, that is number of helium atoms per unit volume, is almost equal to 2.2 into 10 to the power 28 per meter cube. Okay. So when you will substitute all these values and the value of Planck's constant H and Boltzmann constant K, which are universal constant, then after simplification you will get that actually the critical temperature comes out to be 3.13 Kelvin. Actually, we have seen that the lambda transition temperature, that is the temperature at which helium first liquid is transformed into helium second, that is actually 2.18 Kelvin. This is experimental value. You can see that the experimental value of this temperature T lambda at which transition takes place is very close to this theoretical value. Or in other words, actually you should say that this theoretical value of transition temperature 3.13 Kelvin is very close to the experimental value of transition temperature, which is 2.18 Kelvin. Okay. Now, when the temperature of this fluid is between 0 and Tc, that is temperature is not greater than this critical temperature. Actually, in that condition, you will see that any Bose gas shows some specific behavior, and all these things you have learnt in the lecture on Bose-Einstein condensation. So this idea is just a repetition. You have already studied these things. Okay, and you know that in general we consider that there are two energy states or two quantum states. First one is called ground state with energy E equal to 0. This is called ground state. And the another energy states are excited energy states, and for which E is not 0. This is excited states. Okay. In fact, in these two states, the atoms of the Bose gas are distributed. Okay. So according to ideal Bose gas model, you have studied that for a temperature T less or equal to Tc, when temperature is less or equal to Tc, then actually the liquid helium-4 may be considered as a mixture of gaseous phase of Ne particles or Ne atoms in the state E not equal to 0, that is in excited state, and N0 particles in the energy state E equal to 0. Actually, this N0 state is a condensed state. Okay. And that actually form the Bose-Einstein condensate. Okay. And you know that Bose-Einstein condensate has actually some peculiar properties because all the bosons are in the same quantum state, and that's why this helium, the condensed state which you say Bose-Einstein condensate, in this case actually that is nothing. That is the superfluid helium. That is superfluid. Now, you have learnt earlier, I have directly written these results here. You can see that if you consider that in ground state, the number of atoms is N0, in excited state, the number of atoms is Ne, then the total number of atoms N will be equal to Ne plus N0. And you have learnt in the previous lecture that this Ne is proportional to T to the power 3 by 2. Okay, and N, this N which represents the total number of atoms, that is proportional to Tc to the power 3 by 2. Tc to the power 3 by 2. And so you can see from here that Ne by N will be equal to T by Tc to the power 3 by 2. Okay, and so you can say that Ne is equal to N times T over Tc whole to the power 3 by 2. Okay, so this is the number of atoms present in the excited state at a temperature T, but this T is less than Tc. T is less than Tc. Now, if you want to calculate the number of atoms in ground state, that is a state of zero energy, you know that N0 will be equal to N minus Ne. And substitute the value of Ne from this equation to here. So that will be N minus N into this much. So you can take this N as a common factor. And so N0 will be equal to N times 1 minus T by Tc whole to the power 3 by 2. Okay. Actually this as T is less than Tc, you can see. So T by Tc is smaller than 1. Okay, smaller than 1. So this N0 will be actually much greater than Ne, which have been defined in this equation too. So most of the atoms will be in the ground state. In the ground state, if temperature is less than the critical temperature. Okay, and as I have told you that since the large number of atoms are in the ground state, so there will be a condensed phase of N0 particles which occupy the ground state. Okay, and the accumulation of a large number of particles in the ground state is responsible for the Bose-Einstein condensation, as you have discussed earlier. Okay, and this Bose-Einstein condensation in this case corresponds to the superfluid component of helium-2. Actually helium-2 has actually two components. One is actually normal component and the other is superfluid component. Okay. Now you can see that this Ne depends on T, this N0 also depends on T. So let us take what will be the value of these N0 and Ne when temperature is T equal to 0 Kelvin. So you can easily find these values from the result which we have just obtained. Okay, so you can see this N0 by N is equal to 1 minus T by Tc whole to the power 3 by 2. So if you consider that temperature is 0 Kelvin, then see this result. Ne equal to N times T over Tc to the power 3 by 2, and you have taken T equal to 0 Kelvin. So if T is 0, you can see this equation 2, Ne will be equal to 0. Since there is no atom in excited state, so what does it mean? It means all the atoms are in ground state. It means N0 will be equal to N. Or you can see this result equation 3. If T is 0, then this N0 by N, this will be equal to 1. And so N0 will be simply equal to N. It means all the atoms will be in the ground state. And that actually forms the Bose-Einstein condensate, and that also corresponds to the superfluid component of helium-2. Okay, this corresponds to the superfluid component, and it actually shows so many peculiar properties, because you can see that all the atoms are in same quantum state and they will be governed by same wave function, by a single wave function. That's why such a quantum liquid possesses so many peculiar properties. Okay. On the other hand, if you take that temperature is equal to Tc, then what will be Ne? You can see this equation. If T is equal to Tc, see this equation number 2, then you can see that Ne will be equal to N. It means total atoms are in the excited state. So there will be no atom in ground state. N0 will be 0. And it is also obvious from this result, you can see that if you take T equal to Tc, then N0 by N will be what? This will be 1 minus 1, that is 0. So N0 will be equal to 0. So I have mentioned it here. You can see at T equal to Tc, Ne is equal to N and N0 equal to 0. Actually, this is the normal component of helium second. So you can say that when temperature of the helium liquid is less or equal to Tc, okay, then this helium liquid has two components. First component exists when temperature is less than Tc, which is called helium second. It is a superfluid and it exhibits so many strange properties. But when temperature is T equal to Tc or above and greater than Tc, in fact, in that condition, there will be no Bose-Einstein condensation, because in ground state there is no atom. All the atoms are in excited states, and excited state is not only one. There are so many excited states. Okay, so all the atoms in that condition will be not in same quantum state. They will be in different quantum states. And so that component of helium liquid is a normal component, and this this component which is in the ground state of the helium, which is in the ground state, that is actually the superfluid component. Okay, so helium second has two components. I am just briefing it. Helium 2 has two components. The superfluid component is found when all the atoms will be in the ground state. That is when Bose-Einstein condensation will take place. Then that component is called superfluid component. But when temperature is equal to Tc or greater than Tc, then this helium 2 behaves like a normal liquid. It has no peculiar property, and that is called normal component of helium second. Okay, and all these things I have mentioned it here for your convenience, so that you can write down these languages in your notebook, and that will be a very fine notes, a very fine assignment for your examination purpose. So I am just giving this reading here. According to ideal Bose gas model, you know, for T less than Tc, the liquid helium 4 may be considered as a mixture of gaseous phase of Ne particles distributed over the excited states, not state but states, E not equal to 0, and condensed phase of N0 particles which occupy the ground state. Okay, accumulation of large number of particles in the ground state is responsible for Bose-Einstein condensation and corresponds to the superfluid component of helium 2. On the other hand, the atoms in the excited states correspond to the normal component of helium second. So helium second liquid has two components. The when all atoms of helium second are in the ground state, that corresponds to superfluid component, and when all atoms are in the excited states, then they correspond to the normal component of helium second. Okay, so I think you have definitely understand this was a very simple concept, and definitely you have learned each and everything in this lecture, and we will see some more applications, some more discussion on this Bose-Einstein condensation, this Bose-Einstein statistics in the forthcoming lecture. So thank you very much.